So we'll get started here as people come in and settle in and get ready for today. This is day 2 of the ACC Users Group virtual conference. Focus is design and performance, and our session moderator is Riyad Dandan of Dominion Energy. While you have a look at the agenda for today, we'd just like to remind everyone that we want to make this as interactive a session as possible. So please use the chat when you have any kind of questions or comments, or you can raise your hand by hovering over your name in the participants tab. And then we'll call on you during the Q&A or during the open discussion session. Everything went really well yesterday, so we're glad to have everyone back for another 4 hours of presentations and discussion. And we'd just like to quickly introduce the steering committee who put the program together for this year's conference: Andy Howell, Barry Dooley, Riyad Dandan, and Rishi Velkar. And finally, we've got some sponsors for the virtual conference that you can interact with throughout the conference, and you can find out more about what these companies do, who your reps are, on the ACC Users Group website. I'll be posting links to that in the chat. So please take note of all of the resources on the ACC Users Group website. There's quite a lot, and make sure you're signed up for the forums, because we do get some discussion throughout the year. So right now I'll hand it over to Riyad and we'll get today started.
Scott, welcome everyone. Good morning, good afternoon, and good evening for some of you. I am Riyad Dandan, consulting engineer with Dominion Energy in power generation engineering. Thanks for joining us today for the second session for design and performance. We'll start with ACC fan gearbox load measurements presentation by Dr. Danielle Els. I will go over the introduction of the presenters. Dr. Els is a lecturer at Stellenbosch University for the last 25 years. Previously spent over 13 years as test engineer in research and development and in armaments and aerospace industry. One of Dr. Els' research was in advanced dynamics and large system performance measurements and analysis. Dr. Els graduated from Pretoria University, South Africa in 1983 with bachelor's degree in mechanical engineering, received his master's degree in mechanical engineering from Stellenbosch University, South Africa in 1996, and completed his PhD in mechanical engineering in 2009 at Stellenbosch University. Dr. Els, the floor is yours.
Thank you very much. Can everybody hear me? I must just make sure.
Yes, I can.
Yeah, we're fine.
Just share here. Good afternoon, everybody. On this side of the Greenwich line, it's now in the afternoon, so good morning over there. We did a couple of measurements at Matimba and Medupi here in South Africa, and my co-workers Christopher Rensburg and Martin Venter, and I think they're also online today. So just a quick overview. I will just have a background, and then most of the talk is about the measurement. Then some conclusions, and then a little bit about future work that we see. So first of all, we did a series of measurements on the gearbox output at the new Medupi and Kusile power stations. And these stations are fairly new. They are comparable in size. Each has got 6 dry-cooled units of about 800 megawatt. It has got identical Hansen M4 ACC gearboxes, and the big draw card for us was Medupi has got a direct start online, and Kusile as a thyristor type soft start. So here we could compare very well the difference between the two systems. And then just to mention, this is part of a research that we're doing for Sumitomo of Hansen, as it was previously known in Belgium. And I also want to thank the people from Eskom. They did go out of their way to help us and be accommodating for these measurements. So just to show you where everything is, Medupi is up north, close to the Botswana border. It's about 350 kilometers north of Pretoria. It's a beautiful part of the country, lots of wild animals and so on. Kusile is just east of Pretoria, Johannesburg. And then Stellenbosch is down here south in Africa, in the southern point of Africa. Now this is a very old, from the 1600s, a wine country, a beautiful part of the world. So please come and visit us. I think Andy was here about 2 or 3 years ago. This is just a picture of Kusile. I think it's now been finished. It's the only one I could get. So this is, here in the front is the ACC, 6 units. And then just a little bit of background. The Medupi ACC, they've got 34 Howden ELF8 blades and the Hansen gearbox. So this was the test fan that we were using. So it was not an edge fan. And the startup there is direct. And then at Kusile, it's about the same size. They've got the edge fans that's identical to the Medupi ones, and unfortunately we didn't know that before the time. So because otherwise we could have done a very good comparison. They've got internal fans there, which is lots lighter blades, and the interesting one, they've got 9 blades, so it's an uneven number. Again, the same Hansen gearbox, and they've got a thyristor soft start. Now, I've just included this. I'm your good old-fashioned garden variety mechanical engineer, so anything electric is, I need a picture for it. So the thyristor increase the amount of voltage that it lets through. So if there's electrical engineer today, please, if you can enlighten us a little bit better. But you find as it go along, in fact, then the current increase. But this has got a problem from a vibration point. Mechanical engineers don't like vibrations. Nothing in nature like step functions. So the measurements that we did was on the output shaft. So here you can see, if I start from the bottom, the bending strain gauges, we've got 2 pairs of them, 90 degrees. Then a torsion, full bridge torsion strain gauge over there, and then magnetic sensors to pick up the speed, and we need sub-rotation speed. So this was one of the difficult things to achieve, is on this big shaft to measure accurately the speed. And for that we used a tooth wheel. The setup was basically a radio frequency transfer from the rotating hub for the 3 strain gauge pairs. And then we had some accelerometers on the gearbox and the motor to look at relative motion between the two. It is not included in this presentation. This is something that we're still looking at. got some data, quantum X data gathering, and then out to the computer where the number crunching is performed. So the shaft calculation or the shaft speed calculation, this is a difficult thing because we need sub-rotation speed to get a decent analysis. And on that scale, it's quite difficult. So I think we were fairly successful. So the signal from the magnetic pickup and we used a wheel with 60 teeth in it. It looks like this. So the so-called the peaks which we're trying to detect. And in the end, because we are working with a finite time step, we had to interpolate to find those peaks where each tooth came past. So from there, we could calculate then the speed. So this is an example of once per revolution, just to show you what's going on. Have a look at this blue curve. This is because the whole measurement is very sensitive to runouts, materials, accuracy, tolerances, everything. So if you calculate that, you end up with this gray speed calculation. The red curve that you see there is if you go once per revolution. So in the end, by a fairly nice optimization algorithm, we could take out the inaccuracies or the tolerances on the tooth wheel itself, and we end up with that blue curve for the velocity. And you will see that that is about a quarter of a RPM, which the graph, it looks quite rough, but I think that is extremely accurate that we could achieve. So with that, then we could do a proper speed calculation. So this blue one is for the startup of Medupi and the orange one for Kusile. Now the thyristor soft start is about just past 14 seconds, it's on speed. And so if we go to the acceleration side, now this is the interesting one. You will see that for the direct start, there's a very large acceleration of the whole system as it starts up. The thyristor soft start in the end also gives you a value that is comparable to the normal direct start. So you will see also that effect in the torque. So the kind of point that I want to make is that it's not really a soft start in a mechanical sense. It might be for the electric current and so on, but mechanical wise, you don't win a lot with a soft start because the gearbox still experiences that huge startup torque. So this is now what we could do with our accurate speed measurement. Without this, it's not possible to do that. I will come back to this that you see for Kusile at 12 seconds. There's something strange going on there. So the next major measurement that we did was the torsion on the shaft. So it was with strain gauges. You can calibrate the strain gauge simple from strength of materials. The unknown one here is Young's modulus, and Daniel Verbeek from Hansen has given us some values on Young's modulus, and that is for the highest quality of steel. It's still all over the show. So so that is a unknown. I think it makes about, say, a 5% uncertainty in the measurement because we don't know exactly what the specific shaft's Young's modulus is. But let's stay with the average one, and then you can calibrate your strain gauges from that. So the measured startup torque specifically looks like this. So you see for the direct online, this huge oscillations in the beginning. Now that is, there's nothing mechanical to that. We are busy with simulations of induction motors, and that is electric motor identities. It came from the electrical side. It is not the frequency of the fan or the gearbox or anything. That is as the poles of the induction motor start up, you get that large torque peaks there. It dampens down a little bit, and then just before you go to your final speed, you got that peak. Now, the specification for gearbox, for the pairing, when they specify for the ACC, it is normally this at 5 seconds for direct start, for example, where they say, all right, it must survive 40 kilonewton meter, for example. If you go at a soft start, and remember, this is a much lighter fan at Kusile, if we would have looked at exactly the same heavy fan that they have at Medupi, I'm very sure that we will also end up with a value of at least 50 kilonewton meter. So again, the soft start is not mechanically a soft start, it's just a slow start. The other thing that you see as that voltage increase is this kind of very noise that you see as the fan accelerates. And here at 12 seconds, all of them show this huge oscillations there. I don't know what it is. There are no mechanical system in that. That's about 9 hertz. None of the mechanical systems has got a natural frequency there. So that is a strange one, and I think that is probably also a electric effect. After 14 seconds, when the system is running at constant speed, you will see at Medupi, there's a fairly low vibration on torque-wise on the system. While the Kusile one has got a fairly large oscillation, and I can kind of keep myself make myself a profit. They are going to see a lot of breakages on U-bolts on the fans at Kusile in the future. And it's got a lot to do with that vibrations. So the shutdown torque, I think this is also the electric motor as the current has been switched off. You see this effect, and there's quite a heavy negative torque. And the guys that have, I've seen some photos of gearbox breakages at Medupi. They show at the backside of the gear, the non-working side, there are some marks. Now, I don't say it's that, but it's possible that here at shutdown, that the backside of the gear get a kind of a load, negative load. And so this is basically how it, on the shutdown side, the torque that the gearbox experience. The interesting one is if we do a look at the the frequencies. Now this is, if you look at that torque measurement, it's very noisy. But if you use this trick that the guys that looking at the stars, where they take a lot of pictures and they superimpose it and get the average, and that way they find interesting things. You find the same if you go in the velocity analysis. So this is over 3 hours, where you run a lot of smaller windows, get the frequency of that, get the average of that, and in the end, the noise cancels out. And what you see is at Medupi, there are really not a lot of torque noise. So that large fans, and I think there was some tests previously done for GEA in Nexio, and in that instance, Jacques Meiser, I hope he's here today, I did not see anything strange. On Kusile side, at because they've got 9 blades, the blade pass frequency, the 9th multiple of the rotation speed, has got a very large peak. And if you stand on the bridge of the ACC, you can feel that vibration. One or other reason, the blade pass frequency excites a lot of stuff at Kusile. If we look at the torsion load of the fan itself, so if you assume that the aerodynamic load is one or other constant times the square of the speed, and the inertia of the fan, then you can calculate, and this was done with an optimization algorithm, what the fan will see, and that is that equation of the fan torque itself, which is just the inertia and the aerodynamic load. You can find that, and that gives you this orange line. So this is basically what the fan, the effect of the fan on the gearbox. I would say the blue up and down is electric motor effects, and the inertia and aerodynamic load on the gearbox is this orange line. The same goes for Kusile. And again, we see that kind of large resonance type action there just past 12 seconds. So that is physically, we could pick that up by a change in speed, which is, it means it is a very large or a violent type oscillation. This is for different measurements. So Medupi is fairly constant. Kusile, from one to the other, you see differences. I think those blades are the fan guys tell me that the lighter blade and the shorter span blade, cord span, has got is not so constant in weather conditions. So I think that's what's happening here. The final measurement that we did was shaft bending. And in this instance, we have measured in 2 axes, a X and a Y, the bending in order to add it up to get the total bending moment. Again, it is the strain gauge correction factor that we implement just from straightforward strength of materials. And very interesting. So this is something that I was quite surprised at. So the first one is for the Medupi. You could see that. Let me just get back. relative to the shaft. This is for someone that is sitting on the hub. This is what he or she will see. So there is that red point that you see over there. That is basically a unbalance. Now the unbalance can be two things. The one is the mass or the inertia of the blades, and the other one is the aerodynamic unbalance. In other words, as the guys install the blades, it's not necessary that they all have exactly the same angle of attack. And the other thing is, once every maintenance cycle, they tighten those bolts, and if they don't do it in the sequence that the blade manufacturers specify, you can end up changing slightly the angle of attack, and that will increase that unbalance. So it's a sum of mass and aerodynamic unbalance. And you can see, for example, for Medupi, that just that unbalance is about 1 kilonewton meter, which is not ignorable. It is something already. The blue around it, that is, I would say, mostly aerodynamic. As the blades work more or less, you find that the bending on the shaft increase, and this thing walks around. So if you look carefully, you will see how that load, the bending moment, walks around. That's got a nasty implication for the bearings, for the main bearing at the top, because you can find that the loading zone shifts, which is one thing that bearing people don't want. Hopefully this walking around is slow enough that on the other side, if you look at the relative to the gearbox, somebody's standing or sitting on the bridge, what would he or she see? Then this is exactly the same magnitude, but it is now just as it turns around. And you see, interesting, look at the shape. This thing has got definitely a shape. This is more square, four-sided. So this is the Medupi cases, and it's fairly consistent. Kusile on the other side. And please remember, this is much lighter blades. This was done in one day. In the morning, the guys that did the test are here, so we can go back and find the weather. The only change here is weather. This is the first one. Kusile 2 was in the morning, and Kusile 3 was past lunch. So it's the only change there is. And that specific fan, although it's not the edge fan, is still prone to wind effects. So the only reason that I can see is the difference is the wind between two. Unfortunately, I don't have that values available, but we can get it. It is on the logs. The other interesting thing is this got this 5-sided shape. So why, I don't know. It is an uneven number of blades. In the afternoon, there was a lot less of that vibration. So if I go back to Medupi, which is a larger system, blade-wise, heavier, it's got less of an effect than what we see at Kusile. So this was something that I did not expect. And I think for a gearbox guy, this is worrisome, because we've measured close to the hub, So the bottom bearing of that gearbox sees a fairly large bending moment on the shaft. I don't know what they're designed for, but this is quite high. Bending frequencies, Medupi is also on first blade pass or first multiple, which means it is as the blade come along at the same place. So this means that it is basically a shaped load. So it is, I think it's uneven air inlet into the fan that you typically see there. So the whole disc of the fan is bending constantly in one direction. So this is what you mostly see. It's not so sensitive for blade pass at 8 times the multiples and 9 times for Kusile. So basically the conclusions, our speed sensor was very successful. We could measure for, the whole idea was for startup and shutdown to have sub-rotation accuracy, and I think we achieved that for a system that's probably less than $100. A little bit of mathematics around it, but the hardware itself is quite cheap. This shaft torsion, very large torque peaks for direct startup, but low torsional excitation at Medupi. And at Kusile, the soft start, the thyristor type soft start, leads to large torques during startup. So I think this is something that we need to investigate further. Maybe that was only at 14 seconds. Maybe you must double that time. I don't know. I'm not the electrical engineer, so I don't know what the effect of that will be. And then Kusile has got a tendency to get excited for during the blade pass frequency. The shaft bendings, they are unbalanced loads. They're not excessive, so I don't think you need to worry too much about the balancing of the blades itself. If at this stage they just pair them with the same weight, opposite blades. I don't know what they do with the uneven lot. But there is large bending loads on the bearings. And this system is part, let me just get to the next one. We are working on a system dynamic model. So this is basically for Hansen, where we look at the full system. My colleague that's going to talk after me is going to tell you a lot more about this facility at Stellenbosch. But we are looking at the system simulation, especially for gearbox loads. So in the end, we look at motor controllers, the gearbox as a dynamic system, the fan as a dynamic system, and we want to predict a startup like this through, so that we can, before the time, say what's going to happen. That's it basically, and this is just a picture of Stellenbosch. You must agree, it's a very nice place.
Yeah. Thank you so much, Dr. Els, for this interesting presentation. It brought up a few questions here, but we are running out of time here. We are 5 minutes over, 4 minutes over, and I think would be best if you could stay for the general discussion later on to address some of the questions.
Yes, no, good.
That would be fine. Good.
Thank you.
Okay, we're trying to stay on schedule here. This is interesting, presentation, as I said, and it brought up a good point to discuss, especially gearbox vendors. Hopefully, they will participate in that discussion today. Next, we have overview of Stellenbosch University ACC research, and that's presented by Dr. Hans Pertrios. Dr. Hans After completion of his doctorate, which focused on large-scale solar power generation, Hans joined South Africa state-owned utility, Eskom, in 2007. During his time at the utility, he contributed in various project engineering roles, most notably as chief engineer for the cooling and condensing division, and as a lead engineer on the air-cooled condenser plant for the Medupi and Kusile power stations. In 2015, Dr. Petrios joined Delta V Aerospace, where he led the thermofluids division and supported the microgas turbine development project as chief engineer and system engineer. Then in 2020, Hans joined Stellenbosch University as senior lecturer, where he lectures heat transfer to undergraduate and postgraduate students, and conducted research on dry cooling system on power generation application. Thanks for joining us, Dr. Hans, today. Please go ahead with your presentation.
Hi, good morning, good afternoon, and good evening. Okay, can everyone hear me?
Yes.
Okay, I'm going to share my presentation now. Okay, I think that should do it. So yes, good afternoon on this side of the world. My name is Hannes Pretorius, and I am presenting an overview of Stellenbosch University's ACC research. I'm doing this on behalf of myself and my colleagues at the Department of Mechanical and Mechatronic Engineering. As mentioned, we are at Stellenbosch University in the Western Cape province in South Africa. So the contents of my discussion today, I'll give you a little bit of background on our university and department. Then I'll look at some of the resources and testing facilities that we have. I'll discuss our latest research activities and some of the major results from our research team. We'll talk quickly about the research funding and consulting opportunities, and then I'll conclude. So in terms of background, our department has been involved in ACC research over the past 5 decades, and this all started with the late Professor Detlef Kruger, who started with his research in the 1970s already. And many of the large South African ACC's designs and features are greatly influenced by his research, and he always had a strong relationship with industry. So many engineers studied under his supervision, and many of those are now lecturers at Stellenbosch University, and many more are professional engineers in the power generation and cooling technology industry. So we continue to build on this legacy by doing ACC and dry cooling research, heat exchange bundle characteristic testing, ACC and fan CFD simulation, ACC scale fan testing, ACC hybrid deflecmated design and development, ACC fan drive research, and we also still present his postgraduate course in air-cooled heat exchangers and cooling towers. So in terms of the resources and testing facilities at our department, we typically get between 50 and 70 postgraduate students a year at our mechanical and mechatronic department. We also have a link to the Solar Thermal Energy Research Group, which look at the application of ACCs and dry cooling systems for concentrated solar power, concentrated solar technology applications. We have access to a center for high performance computing outside of the university, which has about 32,000 cores, and we use that to perform most of our larger CFD simulations. We also have access to a lab for advanced manufacturing, latest international research publications, and multidisciplinary engineering researchers in the fields mechanical, mechatronic, civil, electric and electronic, process, and industrial engineering. So we also have the following test facilities. We have a ACC scale fan test facility, which is an ISO 5801 type facility. And so you can see the top right-hand corner, you can see a schematic of this facility or a 3D view of it. And it has a 1.5 meter approximately diameter fan. So we test scale fans or ACC fans at smaller scale in this facility, and then we use the results and scale it up to full scale in order to determine the performance of those fans as they would in the ACC applications. So we also have something called a min-water CSP facility. Now that is something that comes from the European Horizon 2020 funding opportunity, which we use to develop this facility. So the picture at the bottom here shows the ACC fan. It's a 24-foot fan, and it's got a gearbox and a motor. And then mounted above it is like a cube-like structure on which is these hybrid deflectmator bundles. So hybrid because it's a wet-dry system, and deflectmator because it's the deflectmator part of the ACC bundles, which is mounted above this the large 24-foot fan. So then we also have an ACC heat exchanger bundle test facility, and we normally use this for confidential commercial heat exchanger bundle testing, but we can also use it for research heat exchanger bundle testing. And then lastly, we do some ACC fan drive testing, which we can also then do in this min-water CSP facility of ours. So we're moving on to the research groups or researchers, and we're going to look at the latest research and their major results. So unfortunately, I don't have a picture of Professor Meyer, but that is a photo of Professor Johan van der Spy, and himself and Professor Meyer normally or often work in tandem on their research. And so they normally look at, or their research fields are in axial flow fan testing and development, ACC system improvement, and ACC modeling. So one of the first areas that we'll look at is the development of tip appendages for ACC fans in order to improve the fan performance at large tip clearances. And so ACC fans are typically run at relatively large tip clearances. And the idea behind this research is that you add a tip appendage in order to improve the fan's performance. This work is done in collaboration with Sapienza University in Rome, and also looks at improving the performance at the designed and higher flow rates. So you can see at the bottom left picture, this picture shows this tip appendage added to the trailing edge and on the tip of this blade. And the idea behind that is to control the tip vortex in order to improve performance. You also then see these graphs, the middle graph and the graph on the right. Their x-axis are maybe a little bit small, but that's the volume flow rate of the fan. On the middle graph, the y-axis is the total to static pressure rise, and on the y-axis on the right-hand side is total to static efficiency. So what we can see, you can see a couple of trends from this graph. So the work was done numerically using CFD as well as experimentally on a small-scale fan. So we can see that from the middle graph, we can see that the CFD results correlate very well with the experimental results. We can also see that there's an increased pressure rise across the fan over the entire flow rate range when adding this tip appendage compared to the standard fan. And on the right-hand side, we can see that the efficiency is increased at the design flow rate and at higher flow rates, again, for the modified fan versus the standard fan. So these researchers do more research. They're looking into the Reynolds number effect on fan performance scaling. So normally when you have a small scale fan, the Reynolds number across the fan blade is not the same as for a large fan in the application. They are doing research in order to mimic the high Reynolds number operating conditions on small scale fans. And they do this by using the free stream or using the effect of turbulence on a airfoil performance that they then correlate to an installed performance. So what they try to do is they use the free stream and they increase the turbulence in the free stream before it even gets to the turbine, the fan blade. And that way they try to mimic this higher Reynolds number operating condition. So the research has been completed, but the results are not yet published. So again, on the left-hand side, we see this aerofoil mounted in our large wind tunnel test facility. And something you cannot see is the free stream turbulence being caused upstream of that airfoil. On the right-hand side, you can see our scale fan test facility, again showing, or this time showing how turbulence is initiated or more turbulence is created in the free stream before it reaches the fan blades. Some further research by these researchers, they are also looking at the development of an exhaust diffuser for an induced draft ACC. And this is specifically for a low pressurized fan. And they are evaluating the performance under wind speeds up to 9 meters per second. So the idea behind the exhaust diffuser is that it tries to regain some of the kinetic energy losses typically experienced by the fan in order to aid performance improvement of the fan. The pictures again on the top left is just a CFD domain for the fan only. In the middle and on the right-hand side, 2 different diffuser designs added to the domains. At the bottom right, we have some CFD results showing the velocity magnitude for this induced draft ACC with diffuser under a crosswind condition. These professors are also looking at the effect of hub configuration on axial flow fan performance. This is a numerical study using CFD, and they're specifically looking at the role of hub vortex structures or the role of the vortices created around the hub on the fan performance. And those pictures here just show some of the hub configurations that they are looking into. Lastly, they are also looking at a comparison of forced draft and induced draft ACC performance. They're specifically looking at a large ACC, so an 8 street of 8 fans each configuration. They're also looking at combining different types of fans, where the fans on the sides, on the edges, are different types than used in the middle, like for example at Kusile, where on the front, on the sides, those fans have steeper gradients in order to deal with crosswinds more effectively. Specifically, they are noting the effect of recirculation is important to consider in this study. Again, this is just a nice plot of some CFD results. At the bottom, we have a graph showing the heat transfer effectiveness of a forced draft ACC and induced draft ACC under primary and secondary crosswinds. So maybe just to note, primary crosswinds means winds that are running along the steam distribution headers, and secondary crosswinds are across those steam distribution headers. So the trends that we can see from their research shows that induced draft ACCs are more susceptible to winds at low speeds compared to forced draft ACCs, whereas induced draft ACCs deal better with crosswinds at lower speeds, while forced draft ACCs deal better with crosswinds at higher velocities. We can also see that secondary crosswinds from these graphs with the dashed lines, we can see that both the induced draft and forced draft ACCs are affected more by secondary crosswinds than with primary crosswinds. And lastly, that induced draft, with this graph at the bottom here, we can see that induced draft ACCs are hardest hit by these secondary crosswinds. Sorry, just the x-axis here is wind velocity in meters per second. We now move over to another researcher, Dr. Mike Owen, and together with his PhD student, Jacques Duplessis, he is researching hybrid ACCs. And specifically, they are looking at a single-stage hybrid dry-wet deflecmator system. So this study is an experimental investigation into this bundle performance characteristics, both in dry and in deluge wet mode. And in the study, they consider a row-by-row thermal and hydraulic analysis. They also look into the techno-economic analysis for a variety of operating and market conditions. And what they found was that you can have a smaller ACC, which gives similar performance at low specific water consumption. On the left-hand side here, we have a schematic of this type of system with the tube bundle, which is a bare tube bundle at the top there. And you have a deluge water system spraying water across the bundle and then collecting in these water collectors to be recirculated again. At the bottom, you have the fan driving the air across that system. The center graph shows the net power generation as a function of the dry bulb temperature, and it shows it for a conventional ACC as well as this hybrid ACC, which incorporates this hybrid deflect motor system. That graph shows the conventional ACC performance in terms of net power generation, and the red and blue graphs show the hybrid system's performance, where the red is in dry mode and the blue is in deluge mode. And you can see once the system switches from this dry mode to wet mode, how it assists the ACC performance during high temperatures. The graph on the right-hand side shows an annualized cost ratio of a hybrid ACC in comparison to a conventional ACC, where they consider on the x-axis the different cost ratios that this hybrid deflect motor could be, from cheap to more expensive, as well as the cost of water is on the y-axis, showing less expensive to more expensive costs for water. And they find below this parity line here, below this line 1, is the feasible cost region for a hybrid ACC. And that was done for different sites across the US. Dr. Owen also looks at the effects of wind mitigation on ACCs, and together with his co-supervisor, Dr. Jacques Meiser of Houden in Netherlands, and their PhD student, Simon Brinkowitz, they conducted an experimental and numerical analysis of the effects of windscreens, wind crosses, and walkways on an ACC. So they combine the windscreens, wind crosses, and walkways in order to find that configuration which is most wind resistant. So they consider two different things. They consider the effect on fan volume flow rate as well as dynamic blade loading. And by using single and multiple objective optimization, they look to find that configuration which is most wind resistant for forced draft ACCs. And they're specifically looking at a smaller scale ACC with 6 ACC fan units and 3 streets. The figure on the left-hand side here shows the experimental setup where air is drawn in order to evaluate the cross-wind effect on a multiple fan configuration, and by looking at these different wind mitigation configurations. That is just some CFD results in the middle there, and I'm not going to go into too much detail, but the graphs on the right-hand side show those optimal ACC plant configurations with these different wind mitigation features built in that they found on the Pareto front. The red and the green dots indicate 2 different sites which were selected as optimal. Lastly, Dr. Owen also looks at improving ACC axial flow fan performance prediction under cross-flow conditions. So normally when large ACC simulations are performed, it's computationally very expensive, and you cannot explicitly model all the fans. So implicit fan models are normally used to model the ACC fan performance for the big ACC. And these implicit fan models have limited accuracy under cross-flow conditions. And so Dr. Owen, together with his PhD student Adam Fenter, is looking at explicitly modeling these fans and then taking those results and interrogating the reasons why there are inaccuracies in the implicit fan models, and also trying to find ways to augment the implicit model to improve its accuracy under crosswind conditions. Okay, so moving on to the next group of researchers, as already my colleague Dr. Els has mentioned. So he works together with Dr. Martin Fenter, and they're looking at the system dynamic modeling and system performance measurements, which was already presented. So I'm not going to go into too much detail. I think he's already mentioned what he is doing in this realm. And the same for this slide, which he already presented as well. So that brings us to myself and Professor Jaap Hofman. We are doing research on natural draft ACCs. And so when we talk about ACCs and indirect dry cooling systems, the ACC or indirect dry system is typically very reliable and relatively insensitive to wind, but typically more expensive than an air-cooled condenser. And ACCs are typically cheaper to install, but have high auxiliary power consumption, is maintenance intensive, and more susceptible to wind. And so we're looking at the natural draft ACC with the aim to combine the advantages of both the ACC and the indirect dry cooling system. So there's been relatively few research publications on this topic, although some contractors have already started offering such systems. So as I'm relatively new to the research arena, we want to research this starting at the fundamentals, really understand the basics, and then moving to more advanced topics. So for this study, our research aims to evaluate the air side flows, looking at the effects of temperature and wind effects on performance, also later looking at the transient effects of these ambient conditions on steam flows, looking at evaluating the steam side flows, the steam ducting, the bundle layout configurations, the air and non-condensable accumulation. We also want to evaluate the effect of parameter variations on performance in order to understand the system characteristics as part of, let's say, a concentrated solar plant, a combined cycle gas, or even coal application. We want to evaluate the scalability of the system, all the way from a large-scale coal system all the way down, CSP, to even smaller systems for solar desalination applications. In future, we also want to have a look at transient startup effects. Then we also, because the cooling tower is such an expensive part of the system normally, we will also want to try and see, are there more cost-effective cooling tower structures that we could use, that we could look at improving the costs of these expensive parts of the plant. And then what's really important for the user is to determine the power station annual power output when implementing such a system, and then also to look at the life cycle cost of a complete power station system and compare it to the alternative cooling systems. Okay, so that is it for the researchers. We'll now quickly look at some research funding and consulting opportunities. When we talk about research funding, or when we establish research partnerships, we want to establish this balance between finding real-world solutions and developing publishable research. And for postgraduate project funding, typically for a master's, it will be $14,000 in total for bursary, and whatever the project-related or project-specific costs are. For a PhD, it's typically $30,000 in total, and then also, again, whatever the project-specific costs are. We can do confidential research and also IP sharing. In terms of consulting services, we can offer fan design, CFD simulation, heat exchanger bundle testing, ACC scale fan testing, ACC fan drive testing, and ACC specification development. So I'd like to conclude and just mention that we are an active research group specializing in ACC and dry cooling applications. We have dedicated test facilities and simulation capabilities, as I mentioned, and we are very eager to partner with industry and develop ACC and dry cooling solutions of the future. So thank you for the opportunity to share our latest research results with you this afternoon.
Thank you, Dr. Petrius. Appreciate that sharing all the research that you are doing and your colleague at Stellenbosch University. There is a lot of research and a lot of, we need time to digest all that. So thank you so much for that. We have a very short time here, maybe 1 minute. Maybe you could answer some of the questions that came about regarding the hybrid, I believe. We have a question from Gary Dicker. Please go ahead, Gary.
Hello, yeah, no, it was just a question about whether they were retrofit options or whether it required a completely new design.
Okay.
So the outcome of the study actually mentions that the hybrid deflect motor system is better when considered as a new build study, and finds that it's less competitive when it's considered as a retrofit. Mike, I'm not sure if you want to also mention something. Dr. Mike Owen is the leader of the study. He's also joining us today, and he could maybe talk a bit more about that.
Yeah, thanks, Alice, and thanks, Gary. I popped something in the chat about that. We didn't do a detailed analysis of, in the latest work about retrofitting. We kind of focused on the new build, and that's because previous work showed the retrofitting to be not particularly cost competitive. But that depends on how you frame it, and what you're looking at. My gut feel is that if you're going for a retrofit option, then maybe just a pure wet part would be okay, because you've already got the big ACC. You just need a bit of a boost, and you can run that wet on and off. Whereas with the new build and the hybrid system is kind of a more elegant system to have that all incorporated in one. And then you also are purely direct cooling instead of needing the surface condenser as well. So whether or not it works out cheaper to do the sort of hybrid as a retrofit versus a indirect wet cooling component, I'm not sure, but I think that might be a better option. So it's something we will be looking at in more detail, but it certainly is you can use it in a retrofit scenario. I'm just not sure if it's the best option for that, but it's certainly an option, and it's got its advantages.
Okay, thank you so much for your comments here. We'll ask more questions, I believe, in the discussion part of the session. There is a lot of points you bring up here, Dr. Pretorius. So we will be hopefully asking questions here later on. So if you could stick around, we appreciate that. Thank you.
Yeah, sure. No problem. Thank you.
Next session here, or next presentation, is extended gear life through dedicated oil conditioning and remote monitoring by Axel Wagner from CC Janssen in the USA. Axel is the sales manager, power and technical manager at CC Janssen. Axel started his career as a mechanic in the oil and gas industry for 6 years, then went on and graduated as a mechanical and chemical engineer in 1994. He's been working in the oil filtration for over 27 years. After getting his MBA in 2000, Axel has developed different business area for filtration products. Axel has been technical and sales manager for the power industry with CC Janssen since 2005. Axel, please go ahead with your presentation.
Yes, thank you, Riyad, and good afternoon to the east and good morning to the west. I want to talk about extended gear life, as mentioned here, and what this can do for you. We do manufacture and engineer oil filtration systems for any liquids, any fluids in your power plants, from turbine oil to the smallest component being the gearboxes, including diesel fuel that you may have as backup fuel on site. Is somebody going to move the slides, or should I do this here somewhere?
You have control of the slides, Axel. Over on the left-hand side, you should see a little down arrow.
Okay. I actually don't have that arrow here. It worked when we tried it. I can just share mine, and then I guess I have better control over this.
Okay, go for it.
Okay. Can you see my screen okay?
Yes, we can.
Yes, we can.
Okay, very good. So I'll be talking about a little bit about the theory, machine components, contaminants, and the wear that occurs. Looking at the applications, machine and oil life extension, Kidney loop depth filtration is what we propose for these components. Looking at example installations and then touching on remote monitoring and the benefits. Basically, what we're looking at, machine components, we have these metal surfaces, obviously, under the microscope. They do look not as even as with the naked eye. And getting particles in between there, that is where, wear occurs. What it all comes down to is the dynamic oil film thickness. We are looking at rolling element bearings here, ball bearings, 0.1 to 3 micron, oil film thickness, gears, 0.1 to 1 micron. So looking at pictures, here we have a very nice oil film, smooth and even, no pressure spikes here that can damage the components. And then on the left-hand side, an oil film with particles where you can clearly see, particles that cause these high pressure zones and obviously wear and tear. When looking at particles, and their visibility, the human hair is about 70 micron. The smallest visible particle for the naked eye is 40 micron, and the particles in question are 1 micron and 3 micron in between those sizes. Now, where do the particles and water and oil come from? They can be built in the assembly or transport, delivered in new oil and fuel generated from wear and oxidation, and then, of course, ingress from the environment. Same basically with the water, plus condensation, temperature changes, and humidity, ingress, leakage from seals, coolers, or accidents, and delivered in new oil, faults in oil handling. There are different forms of wear. One is abrasion, seizing, smaller particle getting in between two horizontally moving surfaces and causing damage that way. Erosion or sandpaper effect, where particles are pumped through or at a high velocity and damaging surfaces that way. Fatigue wear, vertically against each other moving machine components and particles in between, causing wear that way, which is caused fatigue wear. And then, of course, also adhesive wear when the viscosity of the oil is not proper or there is no lubricant available at all. Corrosive wear, water is just as hazardous to a lubrication film or machine components as hard particles, especially in gears or and in bearings when small water droplets get between two high pressure zones, like here, a ball in the bearing shell, exploding, under high pressure, causing hydrogen embrittlement, and also, of course, no lubrication film at all at that point, causing damage to your machine components. Very interesting to see is, the effect of particles and, according to their sizes to your machine components. When looking at the, medium, just, particle size contribution in any given oil sample, you are looking at approximately 10% of all particles are larger than 10 micron, and 70 to 80% of the particles are between 1 and 5 micron. Now, looking at the, or getting back with the dynamic oil film thickness, the particles in question that really have the biggest impact are the particles between 1 and 5 micron, and you have about 70 to 80% of all the particles in any given oil sample in that size. The next graphic I wanted to show here is the McPherson graphic. That reflects, why all these smaller particles have the largest effect. What McPherson did is he was testing the life of bearings, counted the rotations, the revolutions those bearings would hold, and looking at it from a level of filtration. So filtering with 40 micron, 30 micron, 20 micron didn't really make any difference for the life expectancy of that bearing. Filtering at 10 micron, he first doubled the life of the bearings. But most of the benefits of finer filtration here in the range of 1 to 3 micron gave him a life expectancy or a longer life of bearings up to 6 to 7-fold. So just to sum up, not only are most of the particles in the range that can damage your components, but they also obviously have the biggest effect here. So those need to be filtered, and most inline filters that may be in any given machine are usually in the size of 20 to 40 micron. I want to quickly touch on the ISO particle codes here, the ISO particle cleanliness. Don't want to get into it too much here, only to let you know that, when you are looking for particle counts, oil analysis, they usually report in the ISO 4406. And that means they are counting particles larger than 4 micron, 6 micron, and 14 micron. And instead of reporting the number of particles found, they are classifying those. So let's say they have found 14,000 particles at 14 micron. That is in the range of 8 to 16, and they assign a class of 14. Particles, 120,000 particles larger than 6 micron would be a 17 here, and 450,000 particles would be a class 19. The only thing I would like for you to remember is clean oil is defined as a 16, 14, 11, and each time you raise the class or you have a higher class of 1, you actually have double the number of particles. And so if you had a lab result come back as a 19, 17, 14, as in this case, and you previously had one number lower, doesn't sound like much, but it's actually twice as much. Now looking at life extension, this table here was provided by Noria. Those are industry data, from experience. The left-hand column here is, the oil sample that you may have just taken. You look into this column here, and let's say you found a 24, 22, 19, and your goal is clean oil 16, 14, 11, and you're looking at gearboxes, then your life extension factor would be 3.5 if you were able to clean up that oil to where it should be from this 24, 22 to 16, 14, 11. And you could make an argument, since in most gearboxes, obviously you have rolling element bearings, that your life extension factor actually is a 4. And I say that because in most cases that we have looked at with gearboxes is that, first goes the bearing, there is more room for gears to grind. The gears start to grind, and then the gears go. So you can make an argument, the roller bearing is the most important one. Same here with moisture. Let's say you have a 2500 ppm moisture content in your oil sample, and you want to definitely be below 200. Most mineral oils have a solubility of water in oil of around 200 to 400 ppm, meaning it is dissolved and it doesn't show any milkiness. Anything above that, when saturated with water and above, you will see water droplets, and they are the most damaging because, as shown in a previous picture, they can get into the high pressure zones and then explode under high pressure. So the life extension factor here, coming from a 2500 ppm to below 200, you will experience another life extension factor of 5. Now the application. How do we keep that oil clean? We recommend kidney loop filtration or offline filters. And why is that? They are independent. They can always run. There's no disturbance to the system. It has, it can have the ideal flow rate rather than, taking a little slipstream from the pump that may already be in the system. There are no pressure fluctuations. It draws from the lowest point of the reservoir. It removes sediment, and it provides for an ideal oil sample port. What you're getting is the worst case oil quality, but sampled on an ideal circulating point. Oftentimes, especially in wet cooling towers, you have these long legs, coming out of the cell, and you're trying to take an oil sample there. If you don't drain off a gallon or more, you don't really have a good sample there. And with our systems, there's always an ideal oil sample port included, which sits between the pump and the filter. So you're getting the dirty side of the filter, and that is a very representative oil sample. Now, there are different types of filtration, obviously. And most of what you will probably have seen are these typical surface filtration, cartridge type filters. Those are good filters. They can move a lot of fluid at a fairly minimal delta P. The downside of these is that you really only have the surface to capture particles, and they also don't remove any moisture or water. What we do is depth filtration. They're basically very dense cellulose-based filter inserts that filter through a very deep filter, and they hold anywhere between 100 or 200 times more particles than a typical surface type filter. The added benefit of this depth filter is also that it absorbs water. And in the size for your ACC fan gears, it'll be a half a quart of water that it can absorb and about 2 pounds of dirt. This is how a typical filter insert looks like. This is an outside infiltration. The oil needs to go through several inches of this material and then get to the clean side here in the center and going back to your gearbox. It does take care of particles, 3 micron absolute, 0.8 micron nominal, so exactly the range of what is recommended for keeping the dynamic oil film thickness, this dynamic oil film clean. It adsorbs varnish, oxidation products, and absorbs water. So looking at an average of all the filtration systems that we have provided for cooling tower gearboxes, a very, average cleanliness code or dirty code, I should say, in this without filtration is in the low to mid 20s, so 23, 22, 19, much, or close to the one that I showed in the life extension example in that table. And the average oil sample here for gearboxes with filtration installed is a 1511. So you can assume, very, very comfortably assume that you will extend the life of your gears and the bearings by anywhere between 4 to 5. If water is present, even more. Our filter units are designed so that you only have to do an annual filter insert change. This picture here shows a typical used filter insert placed next to a fresh one here in this example. And this one actually had also absorbed quite a bit of water in the cellulose here. Here's an example from an installation on a wet cooling tower. You can, take your oil sample here. It looks very similar to the one at the ACC gear. You have, you can install either a 3-way valve or an assembly here with 2 valves on the suction side of the filter pump and actually draw fresh oil through the filter into the gearbox while it's running. A little bit about remote monitoring. The kidney loop filtration assembly here, and now pictured with an oil condition monitor on the filter itself, is the ideal place to be used for oil condition monitoring, online oil condition monitoring. That is because you have already established a circulation, so you are always getting a representative sample. It draws from the bottom again, the worst case oil sample, but analyzing it in an ideal circulating way here. Recommended for smaller equipment, like in your case with ACC fan gears. That may seem like a lot if you would put an OCM on there, to get a continuous online particle count. It is, of course, helpful, but probably would, not be feasible economically. So what we recommend at a minimum is connect 2 signals to the control room, and that would be filter pump on off and a high pressure alarm. Because it is very safe to assume that when the filter is on and it has not reached high pressure, that your oil is clean. The other option, of course, for critical equipment or larger reservoirs like turbine oil, is the continuous monitoring of the oil quality alongside filter pressure, and if the filter unit is even running. What you get in the standard unit is the ISO particle count, as explained earlier. You will get the water content as measured in relative humidity or relative saturation in percent, meaning that if you are below 80%, you are in the safe zone and there is not enough water present to cause any damage on moving parts. Other sensors are available: oxidation and resistivity. Resistivity especially important for steam turbine EHC systems. Now, looking at what may be gained from continuously monitoring of your oil quality. Here you have a typical example, of a turbine oil, and you see, a very low and steady measurement here over days in the range of, ISO 12 or 13, so extremely clean oil. And then you have a little bump here all of a sudden. And also here down the green line at the lower graphic, which is the raw particles, particles larger than 40 micron. Now, what happened here is simply just adding some oil. Another, thing that you can easily see here is, startup and shutdown of your turbines or other equipment. Everything will now leave a fingerprint. And imagine, just looking at the particle counts here, somewhere in a 10 or 10 to 11 isoparticle count over days, and then here, 14, 15, or 18 here at one peak. Imagine when if you take an oil sample here on June 2nd, you would get one value, or July 2nd, and July 7th, you would get a totally different particle count, sending it off to the lab. And it's hard to, in retrospect, to find out, what happened and why are my results so different. So as a summary of benefits with a dedicated Gearbox kidney loop filter, you can always, clean your oil to an ISO 16, 14, 11 or better. Your oil will always be dry. There's typically no oil changes necessary. Gear oil, it doesn't really run that hot that it will oxidize much, so that you would have to change the oil for that reason, just because it oxidized. There's really no oil changes necessary if you keep your gear oil clean. Another benefit that we have found some customers made use of is using the clean discharge of the filter to add fresh oil to the top bearing. You can use the filter pump to add fresh oil, as already mentioned. You can take repeatable oil samples while the gear is running. Your oil is generally cooler by about 10 to 15 degrees Fahrenheit, just because you are circulating that oil out of the gearbox through the filter and back into the gearbox. Yes, you can add the lubrication to the upper gear bearing if that gearbox is equipped with another, connection on top. You can get immediate alerts for water ingress if the gear seal breaks. What I need to mention in this regard is that, if this filter absorbs water, it takes about half a quart of water, and then it blocks. So it'll tell you exactly when saturated and alert you that way that something is wrong in the gearbox. And it is easy to connect for remote monitoring. There are many case studies and articles on our website, so please, check that out if you are interested. And may I answer any questions?
Thanks, Axel, for this interesting presentation. As we can all imagine, that lubrication is very critical in the equipment in the ACC, specifically gearboxes. And we have, I'm sure, a lot of interest in that. One of the questions that came from Francois, specifically on lubrication in ACC fan gearboxes. Please go ahead, Francois.
Yes, thank you. Actually, I did receive your email. You sent me that the table to show the life improvement of having different cleaner oils. But financially, I mean, I can achieve less than 16, 14, 11, but at what frequencies is it typically then required to change the filters to be practical for maintenance as well? Are these filters then changed once yearly or every 6 months?
No,
What would you say? Because I mean,
Mhm.
from my side, I had some challenges to motivate because initially when I specified I wanted to procure new gearboxes, to say I want a 16, 14 level oil cleanliness,
Yeah.
and it was almost difficult to get it approved because they said it's too expensive to maintain such a oil cleanliness. Um, so if there are other people that achieves less than 16, 14, 11, I would like to get some responses to say yes, we can achieve it. throughout the whole life cycle of the gearbox and not just maybe for the first 6 weeks or a week or so.
Yeah, and when you look at new oil, the average cleanliness of fresh oil is not even suitable for most applications. It's usually an 18, 16, 14. So that would typically require it to be filtered into the gearbox. And if for your case specifically, I would just get one unit for one of your gears and install it and let it run, and show your practical results, your real life results, to justify that. We can guarantee that the cleanliness levels, is going to be 16, 14, 11 or better if that filter runs. And under normal circumstances, if there is no accident, you will only change those filter inserts once a year. And the cost is really, I think in this small size, you're looking at maybe something like $120 per gearbox per year for the filter insert.
Okay. Thanks, Axel. Thanks, Francois,
Mhm.
for that question. Axel, I have a question about, have you had the chance to select or test online continuous monitoring and filtration of a gearbox on the ACC versus intermittent filtration, say 3-4 days, and then you move to another gearbox and do 3-4 days and come back, say 3 months from that and start all over again. What's your experience data that you may share with us here?
Yeah, in general, I see my picture is frozen here. Can you hear me still?
Yes.
Okay. So basically, you have something like a sawtooth cleanliness curve if you do it, with a mobile unit that you move from gearbox to gearbox. And that is actually how many of the ACC gearboxes are being maintained by some of our customers now. They have some mobile filter units that they move around. But in general, you don't reach the 16, 14, 11 continuously. And there's also the added, burden or hurdle, if you will, of, having operators or maintenance personnel moving those units around. And, sometimes they're just really too busy, and then the cart is just, standing somewhere, not really in use.
Okay. Any other questions from the audience? Yeah, we have here also comment from Francois. Please go ahead, Francois.
Yes, thank you. So this is not specifically directed to Axel, but I wanted to know what is typically a good duration in terms of running hours for a new gearbox to reach that point where the gears has been run in, so that you can determine if your gear wear is unacceptably high. Because I do understand that initially you should get some wear and your iron content might be a bit higher than it should be. But after how many hours should it be stabilized if you have if you just have the normal inline filters and you are not running a kidney filtration system?
Okay. Axel?
Yeah, I think that is best addressed to the users. We know that we can extend the life of.
We lost you, Axel.
Yeah, I think Axel's having some technical difficulty. He should be back on in a second.
Okay. In the meantime, we have Richie here. has his arm raised.
Actually,
And
I actually had a question for Axel, but I was just going to
yeah,
mention on
okay.
the same lines for sampling, whether it be possible to have like a sequencing valve, just like our on our boiler chemistry, we have like sequencing valve and one analyzer. So say if you have 40 fans and then or 40 gearboxes with a sequencing valve, you could just pull samples off of each gearbox and sample it that way instead of having like a mobile card. Have a stationary analyzer and somehow pipe that to each of the oil reservoirs to pull the sample out of, and then have like 40 sampling valves maybe, but actuate every like 5 minutes or something, and that way we can have a continuous, you know, oil particle reading. But
Yeah, yeah. The filtration system, like Axel was mentioning, a lot of users use mobile units that will go from gearbox to gearbox because some, and for example, in Dominion, we have large ACC 80 cells, and it's more economical to use a mobile unit to move around all the ACC. Of course, takes a long time, but at least it's get the job done. But I would like to see more data on the cleanness of that oil if we filter it and clean it continuously versus intermittent. So we'll see. Any of the audience have some experience with that oil filtration and cleanness? Maybe they can share their experience with us. Yes, we don't have any. Okay.
Axel is back on, Rishi, if
Yeah,
you'd like to.
I had some issues here, apparently with my connection. I apologize.
Okay, go ahead, Richie.
yeah, Axel had a question. I was wondering if you could have like one, instead of having a mobile unit, could you just have one unit which is stationary, and then maybe have sequencing valves that connect to each of the ACC fan gearboxes, and then every so often to actuate those sequencing valves to pull a sample, or maybe even send it to the filter, so that way you don't have like a mobile card, uh, which is kind of labor intensive. Have you ever had? Do you have any customers with something like that?
Yeah, no, we don't. And there is one main reason for that, and that is that, if you have if you're trying to valve several gearboxes to the inlet and outlet of the filter, you actually have a chance of, drawing one dry and overfilling another if the valves are not, uh, operated properly. And I do understand that, it is, of course, a cost factor if you want to put one filter on each gearbox. Um, but, we are working on a smaller version of this filter, and I think we can probably bring this down in cost-wise to less than $2,000 a piece. The wet cell cooling tower fan gears, they run anywhere between 3,000, 3,500. And for the smaller ACC gears, we can probably provide that for, less than 2,000 per piece.
So you guys
And
are working on a better solution
yes,
for continuous.
a smaller one, correct.
Okay, sounds good. Um, Thanks, Axel. Appreciate that. Nice presentation. Now we'll open question for a general discussion. We can go back to questions that we had early on that we couldn't get to during Dr. L's session here. And it was from I believe, let's see here, Richard Pratcher, please go ahead with your question to Dr. Els.
So if you went with an external cooling fan, you could probably get lower as well. But usually there's the limit was just cooling over the fan motor. So, but those Balder motors were designed maximum RPM of like 90.
Yeah, for a while there was even more.
Okay. Richard. Okay. Maybe is Dr. Els on? We also have another question from Gary Dicker on the torque measurements, directional. Gary? I don't know if Dr. L is still on or not. Scott, do you know if Dr. L is still on?
Yes, he is.
He is? Okay. I couldn't hear him.
Yeah, it's more of a question of the curve that Dr. Els had shown, which kind of suggested that at the end of the acceleration of even the soft start, you end up with this kind of peak in torque. And I wondered if that was probably down to the fact that the acceleration stopped and then you had a kind of effective braking for a short period. And then whether to mitigate that, you just start to ramp down the acceleration towards the end of the soft start, whether that's possible to kind of soften that blow as well.
Over here.
We
Yeah.
couldn't hear Dr. Els.
Yeah, I see that he's online and he's unmuted, but we're just not hearing him if he's speaking.
Okay. Maybe in the meantime, we can move on to another question regarding, well, we still, some of the questions are for Dr. Els, most of them. So, maybe we'll give him a minute here to see if he can reestablish connection.
Hey, Riyadh, this is Andy. Maybe I'll ask a question we can think about in the meantime. I'm curious. This would be from Hannes's discussion, but more for Dr. Owen and for Dr. Reuter, who I know have worked a lot on the hybrid deflegmators. Are there any pending installations, or how much interest has there been in installing this technology in air-cooled condensers as either initial construction or retrofit?
Andy, this is Mike speaking. I'm not aware of any with the hybrid deflegmator, but I think Hanni Reuter will be much better positioned to answer that question. But as far as I know, the sort of hybrid deflegmator system is not something that's being offered as a product yet, but I stand to be corrected on that.
Okay, Hanno, come on if you're able, but I'm aware that two companies are actually offering that. And I did get a call sometime in the last 6 months from I think it was a consultant in India who was interested in what I knew about that, whether that was a technology they should consider. So there is some interest. I also pretty sure I had a communication a couple of years ago that some plant in China had something they were calling a hybrid deflegmator installed on an ACC, but it's hard to get information from China. I never was able to get anything further on that. But
all right. Well, that's very good to hear that there is something happening with that system out in industry. But yeah, again, I think if Hani Reuter is the man who'll know most about that. But yeah, very interesting news for me to hear.
okay, well, if Hanno doesn't get back, we can check with him in the afternoon session as well.
All right. Thanks, Andy. We have a question or a discussion about the Gearbox topic from Chris Samuelson. So go ahead, please, Chris.
Yes.
Share your experience with us about the Gearbox failure that you have.
Sure, thanks. Yeah, hi, this is Chris Samuelson. I'm an engineer with AES in California, and we've got a new plant. This is my first ACC conference. We've got 2 new plants with ACCs. They've been in operation for less than 2 years, and we've had 3 gearbox failures already at the same site. They're all Flender H2NV model type gearboxes. They only operated for less than a year and a half. All had less than 5,000 hours of runtime. One had less than 2,000 hours, and we're getting lower output bearing failures on all 3. They're grease bearings. I'm just curious, I guess, from the group, if anybody else has had issues with this type of gearbox, particularly manufactured within the last 5 years or so.
Yeah, I can start. We have in one of our fleet, we have 60 gearbox on one ACC that has Flender gearbox H2NV 109, and I just confirmed with station engineer this morning that we have not had any failure on the output shaft bearing on these gearboxes. We have been in operation for over 9 years now at that station. So that's one input here on these Flender gearboxes. Anybody on the call here have experienced similar situation?
Yeah, this is Rishi. We have the same gearboxes, the same model at our plant as well. We didn't really see any failures. I mean, they ran fine for a good 12 years before we started seeing failures, but none of them were bearing failures. Mostly like the oil pump has to be changed out, or obviously the filters and the oil goes bad, but nothing catastrophic like that.
Okay, yeah, thanks. I believe that Flender changed their manufacturing location within the last 5 years. At least that's what I heard. So ours are manufactured in China. So I don't know if anybody has gearboxes that are manufactured from the same location.
See. And how many total gearbox do you have on that ACC?
30 on one side and 35 on another.
Okay. And you said grease on that bearing?
Yeah, grease. So a couple of potential failure modes we're looking at. Issues with the grease, whether it's volume or quality, and then the other failure mode we're looking at is overload. Either, could be a range of issues for overload. We know we do have high vibration. We've got high blade pass frequency vibration on almost all fans.
I see. Oh, all fans.
Yeah.
And those failures, just to put things in perspective, those gearboxes, are they perimeters, on perimeter fans or
No, the
interior
ones that are
fans?
failing are actually interior, but we
Interior
do,
fans.
yeah,
All three of them.
yes.
Okay. And I'm sure you are going through the root cause analysis here, and you're gonna take a look at the blade pitch and all the, blade dynamic loading to see the reason for the vibration.
Yep. Yeah, we're going through that now. So it's a process, but
Yep.
I did post a new thread on the forum. So if anybody, hears this and wants to get in touch with me, please do on the forum. I just started a thread yesterday under the Gearbox section.
Thanks, Chris, for sharing that. Hopefully, we'll have some input from other users that will be helpful, especially, like you said, the last 5 years of the manufacturing of these gearboxes. Seems like Dr. L's have an issue with his microphone. It's not working at the moment.
I
So
think it's hopefully now working. Can you hear me, Rayet?
yes, I can.
All right.
Okay. Yeah, we have a few questions early on. We couldn't get to. We ran out of time. The measurements that you have on these ACC fan gearboxes, just to put things in perspective, as far as these measurements were on fans that are, on that ACC for Medupi and Kusile. Any particular location you choose to make those measurements?
At this stage, the measurements was at the fan that was available. So we were asking for edge fans because they are more wind prone, but at this stage, they could only give us a certain fan and we could get in and out. So so South Africa has a problem with not enough power at this stage. So they were not very keen on having us fiddling around there.
So if I understand correctly, these tests were on interior fans.
Yeah, both the stations were on interior fans, yes.
Okay. We have I think maybe that would answer the question for Richard, unless you have another question, Richard. Pretchler. Okay.
I think there was one question regarding the at the startup talk
Yes.
of the soft start, and unfortunately there's a mathematical thing. If you have a step function, then you find that typically that type of reaction. It's like driving with your car over a speed bump. If you have a change in velocity, for example, you find that. So you need to do it over a very long time if you want to get rid of that peak.
And I'm trying to remember during your presentation, was there dynamic loading on the blade while you're doing the measurement? Have you noticed any changes on that? Was that taken into account?
At this stage, we only had to look at the gearbox loading.
Okay.
The fan blade itself was not instrumented. So we could only look at bending moments and torque on the shaft itself. So we were focusing on gearbox load, not so much fan load. So it's only secondary that we find, say for example, that unbalance and that type of thing.
And when you saw that unbalancing on this concern you have on the bending moment on the shaft output shaft on the gearbox, did you go back and see the pitch on these fan blade and the tracking on these blades?
No, unfortunately, we only had 1 day available, so we had to come in, instrument the whole thing, and do the test the next day, and then get off site. So it was not a thorough investigation of the blades itself. As I've said, we were looking for gearbox loads, and in that regard, we did get very good information, especially. I see Francois Nel is here. He can vouch for a lot of failures from the bottom bearing and that type of thing. So, and I think we can, from this data, kind of point to the excessive loads on the bottom bearing of the gearbox.
Yeah, I'm scrolling down here to see if any new question came up.
Hannes has his hand raised, so he can unmute himself.
Hi, Donnie. It's Hannes speaking. I just had a question regarding, you mentioned in the presentation that you saw some marks on the opposite side of the non-driving gear flank. I was wondering whether, if I remember correctly, and maybe Francois de Pre can help me out, I think Medupi and Kusile gearboxes have got a backstop to prevent windmilling in the wrong direction. I was wondering whether you think that could be the cause for that marking on the wrong side of the flank, or whether you think it can't be and it should be due to sort of the oscillations during driving the fan.
Hannes, I think if I look at that there's a fairly large negative torque that the gearbox experienced during shutdown. The windmilling or the anti-windmilling effect, I'm not sure if that's very low torque. So it might be if that thing is standing for a long time, kind of vibrating, but I don't think it is. I'm quite surprised about the high negative shutdown torque. I didn't expect that.
Okay, thanks.
Thanks, Dr. Els. Appreciate your staying on to answer some of the questions. We are reaching our end session here in the morning. Folks. Thank you guys. Thank you all for joining us. Scott, do you want to take over now for the break? I think, or do we have a minute here? Go over some business you want to take care of.
Sure. Break time coming up for an hour before we start the second half of today's presentations and discussion. I just posted a link in the chat to the ACCUG virtual conference webpage. If you have some time to dive into that and connect with the sponsors and presenters from today. And we'll see you back here in an hour, and I'll just flash up the the agenda for the rest of the day, starting with latest axial fan design, then windscreen, B-frame versus A-frame, and a performance comparison between co-current and counterflow ACC tubes. So we'll see you back here in an hour, and we hope you can join us.
Thanks, Scott. We'll see you in about an hour. Thank you.
Thank you.
Thanks all.